So after talking about capillary dynamics, we now need to look at how these relate to lymphatic drainage. So if we think about the forces that were involved in capillary dynamics, we're talking about the net filtration pressure being dictated by the hydrostatic pressure of the capillary minus the osmotic pressure working in opposition to it. Remember that the hydrostatic pressure of the capillary is equivalent to the blood pressure because it is the force of the blood being applied to the wall of the vessel. So when we look at our schematic, we have our arteriole at the front of the bed. We have smooth muscle, small layer of smooth muscle still in the wall in the tunica media. The tunica externa is serosa, and the tunica interna is our single layer of endothelium. As we go into the capillary bed, we're going to go down to a single layer of endothelium with a basement membrane before we exit via the venule, which is our endothelium on a thicker tunica externa or serosa. As yet we don't have any smooth muscle of a tunica media. Now interwoven into our tissue bed, into our capillary bed, are blunt-ended vessels called lymphatic capillaries. And the premise of the lymphatic capillary is to remove excess fluid from the tissue. So as part of the capillary dynamics, what we had was fluid being forced out into the tissue on the arteriolar end, where the HPC, the blood pressure, is the greater of our two forces. So we had a positive net filtration pressure, and that fluid then circulates as interstitial fluid through the tissue. Now the circulation is constant through the tissue, and it allows us to maintain concentration gradients. So we have nutrients traveling into the cell and wastes coming out of the cell. As we go into the venular aspect of the capillary bed, so the low pressure side, then we have our flow going back into the capillaries because our osmotic pressure is greater than our hydrostatic pressure. So we have a negative net filtration, so fluid will flow back into the bloodstream and then leave. However, there is always going to be some excess fluid, and so that excess fluid, as it's moving through the tissue, generates its own force, which is called the hydrostatic pressure of the interstitial fluid. Now, to help us remove that extra fluid, we have blunt-ended lymphatic capillaries that are embedded into the tissue. Now, the lymphatic system is a one-way system. It starts as a blunt-ended vessel in the tissues and is going to make its way back through all of our appendages, back to the trunk, to drain into the brachiocephalic veins, just as the internal jugulars are coming down. So the primary premise of the lymphatic capillary or the lymphatic system is to help us with that drainage of excess fluid, and then once we are in the system, we are also going to look at its second function, which is part of immunity. Now, how the fluid gets into these blunt-ended vessels in the first place is through that manipulation of the hydrostatic pressure. So our blunt-ended vessels have these little gaps in them. These are mini valves. The mini valves allow for one-way flow. They have small sort of anchoring protein that attaches the two sides of the valve, and what happens is that as fluid circulates, the hydrostatic pressure is going to be applied to one side of the valve to push it open, so you push it inwards, and the fluid will end up into the lymphatic capillary. So our excess fluid is going to be pushing its way through all of these mini valves into the vessel. Now, as they do so, as you get increase how much fluid is in there, as fluid passes by, it will be exerting a pressure on the underside of the valve. So if you imagine that we have sort of the a proximal end and a distal end. If this is the proximal end, so closest to where we start, this is the distal end, the fluid is going to be travelling distally away from the source of, from its origin, and the pressure once we are inside the vessel, let's call it the hydrostatic pressure of the lymphatic capillary, once we are inside the vessel, that pressure is going to push up underneath that proximal side of the valve and essentially force it shut, because we're going to push it so that it does this. And as a result, there is going to be no fluid escaping. For fluid to enter, the hydrostatic pressure of the interstitial fluid has to be greater than the hydrostatic pressure. To ensure that fluid gets into the lymphatic capillary, you need to have greater hydrostatic pressure of the interstitial fluid pushing on top of the valve, and it has to be greater than the pressure inside the lymphatic capillary pushing underneath the valve. As you go through the tissue, the amount of fluid that is in this lymphatic vessel is going to mean that this gradually will get larger, this pressure, and it will soon become greater than the pressure of any of the fluid in the tissues. At that point, we are going to flow through the lymphatic capillaries and continue our journey through the lymphatic system.